Good morning, everyone. My name is Stathis Maneas, and today I'll present the study we've done at the University of Toronto in collaboration with NetApp on the reliability of solid-state drives, or simply SSDs, in large-scale enterprise storage deployments. So, why SSDs in particular? Over the last several years, the storage landscape has changed. Storage companies have been using more and more SSDs to store their data, transitioning from traditional hard disks to flash devices. Therefore, as more and more data is now lives on flash, the reliability of data directly depends on the reliability of the underlying NAND. So, what do we know about flash reliability in production? Over the last several years, 4 field studies have been published involving distributed data center storage systems. However, none of these studies focuses on enterprise storage systems. So in these systems, the drives, workloads, and reliability mechanisms are different. For instance, enterprise storage systems usually contain high-end, more reliable drives, and reliability is ensured through RAID instead of distributed storage codes, for example. In our study, we explore the reliability characteristics of SSDs in the field when deployed in enterprise storage systems, and we include several different factors that haven't been studied before. For instance, we explore the reliability characteristics of 3D TLC NAND. Also, our dataset includes large capacity drives that are capable of storing a few terabytes of data. And also in our study, we explore how different firmware versions can impact reliability. Finally, we explore temporal correlations and failure correlations within RAID groups. Our data set is based on a large population of NetApp's production systems, or also called filers, which send weekly telemetry data. This data includes information reported by each individual SSD, along with information about the corresponding system. In total, we monitor 1.4 million SSDs for 2.5 years and present our findings. Our data set is very rich and contains drives from different flash technologies, spanning all the way from older SLC drives to eMLC and the most recent 3D TLC drives. For eMLC drives in particular, we divide them into consumer and enterprise class eMLC drives. The SSDs come from 3 different manufacturers, and in total we have 18 different drive models, some of which are shaped under a different capacity. When it comes to age and usage, our data set is very rich and has a wide range of values, and also it has several different system configurations. For example, we have small systems that contain a few SSDs and are capable of storing a few terabytes of data, whereas we also have larger systems that have hundreds of drives and which are capable of storing a few petabytes of data in total. So we begin our study by considering the different replacement types. Issues can be detected by different subsystems, and basically they can be reported by a drive, the storage layer, the file system, and so on and so forth. So when an issue is detected, then the corresponding drive is getting replaced. In this table, we observe the different replacement types that we have in our study. On the left, we have the different categories. So basically, we group all the different replacement types into different categories and order the categories based on their severity. So SL1 is the least severe one, which contains predictive failures, which basically indicate and predict that the drive is about to fail, so the drive is proactively getting replaced. Whereas the SL4 is the most severe category, which basically contains those cases where something is wrong dramatically with the drive, so it has to be replaced immediately. So how frequently do all these types occur? As we observe, SCSI errors dominate, as they comprise 1/3 of all our drive replacements. The next, we also observe that SL1 category as a whole basically comprises another 1/3 of our replacements. However, as I mentioned, this category contains those replacements that are less severe and are merely preventative based on predictions. Finally, we also observe that SSDs rarely become completely unresponsive, as the corresponding percentage is equal to 0.6%. So we continue our study by focusing on the annual replacement rate, which is defined as the number of failed devices divided by the total device years. In this figure, we show the annual replacement rate of all the different drive models in our study. As we observe, there is a wide range of replacement rates, ranging from 0.7 all the way to 1–2%. The average replacement rate across all these drives models is equal to 0.22%. Someone might wonder whether these replacement rates are actually low or high. So to help answer this question, we put our results in perspective with related work, and basically the first thing that we observe is that the highest replacement rate in our study basically lies at the low end of the range reported for Google's data center drives, which experience replacements from 1 to 2.5% every year. When we compare the replacement rate for the SSDs in our study against numbers reported for hard disks, we observe that the SSDs have significantly lower replacement rates, as the numbers reported for hard disks are usually equal to 4.5% on average, and worst case, they can be up to 20%, indicating that when we compare it with the replacement rates in our study, this can be up to 2 orders of magnitude higher. In our study, we consider several different factors and explore how they impact flash reliability. Due to time limitations, I'm going to discuss only a few of them, but I would really like to refer you to our paper for our detailed analysis and all the different observations. So first of all, when it comes to flash type, SLC drives are the most costly drives, but in return, they are expected to be associated with lower failure rates compared to eMLC and 3D TLC. In this figure, we show all the different replacement rates in our study associated with SLC and eMLC drives, and this time we use a different color for each flash type. So green color corresponds to SLC drives, the red color corresponds to consumer class MLC drives, and the blue color corresponds to eMLC drives. So we observe that SLC is not always better than MLC drives, because as we observe, the SLC drives on the left sometimes have a little bit higher replacement rates compared to blue bars. This observation is consistent with the results reported for Google's data center drives as well. In our study, we're also interested in exploring the reliability characteristics between consumer and enterprise class MLC drives. And however, in our data set, we have only one cMLC drive model, represented by this red bar over there. And based on this single data point, we observe that its replacement rate is surprisingly lower than several replacement rates associated with other enterprise class drives. Finally, when we consider 3D TLC and compare their replacement rates with the other flash types, we observe that they have the highest replacement rates in our study. So the next factor whose impact we explore is lithography. So when it comes to lithography, the common expectation dictates that higher density SSDs are usually associated with higher replacement rates. To separate the effect of flash type, we compare models with the same flash type. So here we have two different figures, one for eMLC and one for 3D TLC drives. So once again, the y-axis shows the annual replacement rate, but this time the x-axis contains the different replacement categories that we have in our study. Once again, the categories are ordered based on their severity, with SL4 being the least severe one and SL1 being the most severe one. So basically, in these figures, what we do is we explore the different replacement rates while breaking down by different replacement categories and also distinguishing between the different lithographies. Blue bars correspond to higher densities, and red bars correspond to lower densities. As we observe, the common expectation is actually verified for eMLC drives, as blue bars are consistently larger, are consistently bigger than red bars for all replacement categories. However, when we look at 3D TLC drives, we observe that the trend is actually reversed, as blue bars, which are associated with more compact, more dense drives, are actually smaller than the red bars. Moving on, age affects the reliability of SSDs as they have a finite number of PE cycles they can consume before wearing out. So the next factor whose impact we explore is usage. In our data set, each SSD reports the number of PE cycles it has experienced so far as a percentage of its PE cycle limit. The PE cycle limit is a number specified by the manufacturer and indicates the time after which the drive becomes unstable. So once again, we distinguish between eMLC and 3D TLC drives, and this time with a red color, red bars represent drives that have seen less usage, whereas blue color represents drives that have seen more usage in their lifetime. As we observe, for eMLC drives, the infant mortality is evident as red bars are consistently higher than blue bars regardless of the replacement category. When we look at 3D TLC drives, the differences are less pronounced, indicating that other effects are at play, such as capacity or age. So for this reason, we explore the effect of age in the next slide. We define age as the number of months a drive has been deployed in the field. When it comes to age and failure rates, common reliability models assume that assume this bathtub curve for the failure rates. Specifically, the bathtub curve indicates that failure rates are high at the beginning of a drive's lifetime for a short amount of time, then they quickly stabilize for a larger amount of time before they start increasing towards the end of a drive's lifetime. Here, what we calculate is the conditional probability that a drive will fail in a month X. In other words, we calculate the conditional probability that a drive will fail in month X, considering that it has survived month X minus 1. The blue line corresponds to 3D TLC drives, and the green line corresponds to eMLC drives. Surprisingly, we observe that infant mortality can actually last for more than 1 year, which is in contrast to the common bathtub curve assumed by a reliability model. Also, we observe that it also takes another 6 to 12 months to stabilize. The shape in our the shape and the different time intervals in our case are much different compared to the commonly assumed bathtub curve. Finally, someone might wonder why we don't see an increase towards the end of the drive's lifetime. However, the majority of the drives in our study are underutilized, so they haven't reached their end of lifetime yet. Finally, we explore the effect of firmware versions on flash reliability. Considering that firmware varies across manufacturers and drive models, we compare individual firmware versions within the same model. We denote the first firmware version as FV1, the second firmware version as FV2, and so on and so forth. Note that most SSDs have the same firmware version over our 2.5-year observation window. Also, to avoid the effect of other factors such as age and usage, for this particular part, we consider SSDs that have seen less usage, specifically less than 1% of their PE cycle limit. So in this graph, we have the different replacement rates associated with different firmware versions, and we compare the replacement rate of individual firmware versions within the same drive model. So in this particular case, this drive model has drives who has basically 3 different firmware versions in our observation window. So when what we basically observe here is that the firmware has actually a tremendous impact on the drive's reliability, as earlier firmware versions can be associated with up to a magnitude higher replacement rates compared to later firmware versions. This result basically highlights the importance of firmware updates, and which should be made as easy as possible for clients. Note that our results remain exactly the same, even if we focus only on the 70% of the drives whose firmware version hasn't changed in our observation window. In the last part of the presentation, I'll be discussing about failure correlations within RAID groups. Double failures and multiple failures in general, when occurring within the same RAID group, have the potential for data loss. So the first thing we wonder is, how frequently do double failures occur? And the answer is that we observe that 2% of our RAID groups see at least one failure in our observation window. So the next question that we ask is, how frequently, how soon the second failure takes place after the first one has already occurred? And in this figure, what we show is the cumulative distribution function of the time difference between successive failures that have taken place within the same RAID group. And as we observe, the second failure commonly follows in a very short amount of time after the first one. In particular, in 46% of all these cases, the successive failures occur on the same day, suggesting that temporary correlated failures are actually common. When we calculate the probability that a RAID group will experience a follow-up failure within 1 week after the first failure has occurred, we find that probability to be equal to 2.54%, suggesting once again that failures are quite correlated. So how does that probability look when we consider the size of a RAID group? Someone would assume that that larger RAID groups would be associated with higher failure rates exactly because they have more drives. In this figure, what we calculate is for different RAID group sizes, and for each RAID group size, we consider all those RAID groups that have experienced at least one failure in our observation window, and compute what percentage out of them experiences a follow-up failure within 1 week after the first. And interestingly, what we observe is that the chance that a follow-up failure will occur does not show a direct relationship with RAID group size. In fact, larger RAID groups do not necessarily have a higher follow-up failure, a chance for a follow-up failure. So to conclude, in our work, we study the reliability characteristics of SSDs in the field when deployed in enterprise storage deployments. Several of our observations contradict common expectations. For instance, we observe a long period of infant mortality, which can last for more than a year, and it takes another 6 to 12 months to stabilize. Second, when it comes to lithography, we observe that higher density drives not always experience higher replacement rates. Finally, when we compare the different flash types, we observe that SLC is not always better than eMLC. Regarding firmware versions, we showed that they have a significant impact on replacements, and our suggestion is to make firmware updates as easy and painless as possible in order for customers to be less reluctant to apply all these firmware updates. When it comes to RAID groups and correlated and failures, we observe that there is actually a temporal correlation between successive failures within the same RAID group. However, we don't have strong evidence that the chance of a follow-up failure is clearly correlated with a RAID group size. Our observations for temporarily correlated failures within RAID group also highlight the need for a different data loss analysis, which has to take into consideration all the different correlations that exist within RAID groups. Finally, in our study, we have considered several other metrics and factors that I didn't have enough time to present. For instance, we explored the effect of capacity, and once again, I'd like to mention that we have extremely large SSDs that can store up to a few terabytes of data. We consider bad blocks, spare blocks consumed, and so on and so forth. And finally, we also perform statistical tests in order to basically highlight the significance of our results. Thank you very much for your time, and I would be more than happy to answer any questions that you might have.
Questions?
Okay, let me.
Yeah.
Hi, very interesting observation.
Can you please give your name and affiliation first?
Just giving it.
Cool.
I'm Janki Bhimani from FIU, Florida International University. I was curious about, have you explored the reason behind infant mortality, and can you comment on that?
Basically, in the graph that I showed, what we wanted to see is basically when we consider the age as a factor, right? How does the shape of the lines looks like compared to like the common expectation of the bathtub shape, right? So in that graph, we consider all the different replacement types that we have in our study, right? So basically, so basically what we wanted to see is that regardless of the replacement type, how does the failure rate looks over time?
Yeah, but I guess my question is more about why do we have infant mortality? Did you look into that?
There are different factors that can result in a higher infant mortality, right? It can be related to the workload. It can be related to the drive model. Sometimes firmware versions can be like more prone to failure. So there are different other factors that can impact infant mortality.
Okay, thank you.
Hi there, Keith Smith, MongoDB. I'm interested in the statistic about the high rate of a second failure when you have one failure in a RAID group. Do you have data on the probability of a third or fourth failure? Because I'm wondering if this is a problem we solve with erasure coding and sufficient redundancy there, or if we need to be prepared for an epidemic failure that takes out entire RAID groups.
Yeah, this is a very interesting question. So in our observation window, we've seen only a couple of cases where like 3 consecutive failures have occurred. And so we don't have enough data on that. Yeah, we haven't seen any cases with 4 successive failures.
Well, that is data. There's no, it doesn't happen. Yeah, thank you.
Thank you.
Peter Desnoyers, Northeastern. Staying on the topic of the correlated failures, I mean, that graph was fascinating. I mean, clearly the drives in the small RAID arrays don't have some sensor telling them that you'd be really in trouble if they failed, so let's fail. But, I'm wondering, do you have information on power events or other things that, for instance, might be correlated with big versus small installations?
Yeah, that's an interesting observation. So so currently what we're working on is basically we are further exploring correlated failures within RAID groups. So we are trying to collect different pieces of information that that can help us answer all those interesting questions, right? And and one of the things that we consider is basically, okay, when one failure has already occurred and a second failure has taken place, what are the different reasons behind that, right? Is it the same replacement type or is it something different that has taken place? But I don't have, we are actually collecting all those data, so yeah.
Thank you.
Quick, my prerogative here, I'm just going to add drive model as a possible thing. Maybe the small, remember that given the wide variance in reliability, maybe the small RAID groups happen to have less reliable drives.
Yeah, that's another possibility as well, yes.
Joe Wen from Daychem. So I'm also interested in the 46% first, I mean the second drive fail at the same day. So I'm wondering, like, when you do this failure rate study, does that also include, I mean, like, is it complete failure, or do you also include the things like a SCSI failure? I mean, like, you have a bunch of failures, right? So do you also include those into picture, or it's just like completed this drive dead?
So this graph is generated based on all the different replacement on all the different replacement events that occurred in our study. So what we defined as replacement is basically all those cases where something is wrong with the drive And as in the previous slide, I showed all the different replacement types that we have. And basically, we consider all those cases where the drive is taken out and is replaced by a spare drive. So this graph is basically all the successive failures that we consider here are based on that definition of replacement.
So basically, if smart's data is wrong, like they mispredict, and then you will take it out, and then assume that they fail the same day.
Yeah, so in that case, yeah, if predictive failures are, let's say, if the thresholds that we specify or the different criteria are, let's say, strict, then yeah, it might be that a drive is taken out due to a predictive failure, and it might not be, let's say, a hardware error or something more strict, but yeah, we do include all those replacement failures in this graph. All these predictive failures in this graph.
Hi, Sarah McAllister, CMU. I was wondering if you looked at failure rates when you had multiple factors coming into consideration, say that you had a high density disk and it was also on various different firmware, like what was happening between those correlations?
Okay. So the question is basically how...
So basically like looking at the correlations between multiple factors.
Yeah. So when we explore the effect of one factor and in different parts of our study, we try to minimize the effect of other factors, right? So that's why, for instance, for firmware updates, we try to take the effect of age and use it out of the, out of that part in order to basically avoid their effect and basically avoid adding bias to our results, right? So. Yeah, so for the different parts in our study, we try as much as we can to focus on one particular factor and basically explore each own impact. But yeah, for different parts, we are also, as you mentioned, yeah, we explore different factors and and explore their combined impact on reliability.
Okay, thanks.
Thank you.
Last question. Unfortunately, we do have to let the next speaker goes.
Hi, I'm Doug Santry, NetApp. On that histogram where you normalized for failure rate and the x-axis were models, SSD model numbers, how was the x-axis sorted? Was it lexically or a year of introduction of model drive? I'm just curious to know if any kind of correlation between newer drives are getting worse or older drives were worse.
So here there is no, let's say, explicit order on among the different drive models. So yeah, so this is, let's say,
they're just classes then.
Yeah. So yeah, this is just
right.
Yeah.
Okay.
There's no
Thank
order.
you.
Thank you.
All right. So thank you very much for that presentation of the
Thank you very
best
much.
paper award-winning paper.